Right, so in the previous video, we were looking at the experiments that kind of led to the discovery of certain subatomic particles and increased our understanding of the structure of an atom. So what we're going to do in this video is kind of dive deeper into how are those subatomic particles related to one another in the atom. What do they kind of tell us about the atom in terms of the identity of the atom? So just to kind of recap what we know about the atom so far. So think about what you can remember from the experiments. What do we know about the structure of the atom? What do we know about the pieces that make it up? And so far, what we've talked about, if we think about Thomson's experiment, he discovered the electron with the cathode ray tube experiment. So we knew that there was a negative piece of it, which implied that there was a positive piece as well, since it's a neutral atom overall. And then with Rutherford's experiment, we determined that the atom is mostly empty space with just a very small positive center. So if we actually took an atom and just blew it up to the size of a football stadium, so if you think about the stadium where the Seahawks play up in Seattle, that could be the size of an atom. And if that was the case, the nucleus would be the size of a single blueberry. So we could just put a blueberry on the middle of the field, and then the distance from the center of that stadium to the outside would be essentially the radius of an atom. So it's going to be mostly empty space between those 2 points. And then with the subatomic particles themselves, the nucleus, so if we think about that tiny blueberry in the center, we're going to have protons and neutrons there. So we've got our positive piece, and then neutron, if you just think about the beginning of that word, neutron, kind of sounds like neutral, because we're not going to have a charge at all. And then on the outside, we've got the negative electron. So we'll kind of get a better understanding of the electrons in one of the later chapters in terms of kind of how are they exactly arranged and how does that affect the properties of different elements. But with the electron, that's just going to be the exact opposite charge of the proton. So that's why atoms in general, or I should say atoms by definition, are neutral, just because they're going to have the same number of protons and electrons with equal but opposite charges. So you can see the actual charge in coulombs here, 1.602 times 10 to the negative 19th, and it's just negative if it's an electron, positive for the protons. But to make it simple, we generally just refer to an electron as a -1 charge, proton as a +1. But these are just the actual values in coulombs. And then in terms of the mass, protons and neutrons, a lot of the times we're just going to kind of round those to 1, because you can see there they're pretty close to 1 anyway, just off by a couple thousandths of an atomic mass unit. So they're very similar in mass, and that was confirmed in Chadwick's experiment where he discovered the neutron. But then the electron, you can see, is much, much tinier. So it's about 3 orders of magnitude smaller there. So that's why when we're looking at the subatomic particles, we can sometimes, so remember the squiggly equal sign just means sort of approximately equal to. So the proton is approximately equal to the neutron in terms of mass, and they're both approximately equal to 1 atomic mass unit. And then since the electron is so tiny, even compared to those already tiny particles, we sometimes just ignore the mass of electrons. So they're not massless, they are matter, so they do have some amount of mass, you can see here. It's just a very, very small amount. And then when we're looking at the atom, we can use the relationship between those subatomic particles, and particularly how many of each of those particles do we have, to describe that atom in terms of the identity of it. So atomic number is just equal to the number of protons. So that'll always be how we identify an element. You can see here an atom with an atomic number of 8 is always oxygen. So if we have exactly 8 protons in an atom, it's always going to be oxygen no matter what. We could have a different number of neutrons and electrons, but if we've got 8 protons, it's always oxygen. If we had 7, it'd be nitrogen. 9 would be fluorine. So the atomic number is always going to give us the number of protons, always give us the exact identity of that element. And then if we think back to the chart here, again, we're essentially considering protons and neutrons to be equal to 1 mass unit, electrons 0. So when we're thinking about the mass number, how much does this particular atom weigh? We're just going to be focused on those two particles in the nucleus, so the protons and the neutrons. And then if we ever needed to figure out the number of neutrons, if we think about it here, atomic number is just protons, mass number is protons plus neutrons. So the difference between those two would just have to be the number of neutrons itself. And then also with this atomic number, if we're thinking about a neutral atom, so again, neutral, balance between positive and negative, protons are +1, electrons are -1. So if it's a neutral atom, the atomic number is also going to be equal to the number of electrons. But with these atoms, in some cases, we're going to see that they're going to gain electrons. Other cases, they're going to lose them. So instead of being a neutral atom, we're going to have what's known as an ion, so positive or negative. And in that case, we need to figure out the exact charge of it. If we know the identity of the atom, we'll always know the number of protons. And then if we know how many electrons there are, we can figure out the actual charge of it. So let's say if we had oxygen, we're always going to have 8 protons. But if we had 10 electrons there, now we've got 2 extra negative charges. So we would just have a -2 charge there. Or conversely, if we know it's oxygen, 8 protons, but if we know we have a -2 charge, that means we just have 2 additional electrons. So sometimes that can be, if we're not thinking about it in terms of this equation, we're just thinking about the number of particles. Sometimes if we hear a -2 charge, there's a couple ways you could think about. We could have 2 less protons, but that would change the identity of the element. So when we're thinking about these charges for a particular element, it's only going to be by gaining or losing electrons. Because if we gained or lost protons, we would be changing what that element is. But with it, if we've got a -2 charge, sometimes people think that means we lost 2 of those electrons. But since the electrons themselves are negative, that means we gained 2 additional ones. So a negative charge means extra electrons. A positive charge means we lost electrons, or that atom lost electrons, I should say. So if we look here, you can see insufficient iodine in the diet can cause enlargement of thyroid glands. So that's why oftentimes if you look at salt, so it's not all salt, but a lot of the times they'll say salt is iodized, so that we can make sure that you're receiving enough of the iodine you need for a healthy thyroid. But if we look at the question in the second piece here, the addition of small amounts of iodine to table salt has essentially eliminated this health concern in the United States, but as much as 40% of the world's population is still at risk of iodine deficiency. The iodine atoms are added as anions, and each has a -1 charge and a mass number of 127. We want to determine the number of each of those subatomic particles in one of these iodide anions. So with the iodide, you can think about it where table salt is sodium chloride. When it's iodized, there might also be potassium iodide in there, just to again, make sure that you're getting that iodide in your diet. But with this one, again, we're told the charge, 1-. We're given the mass number, and then we're told what the element is. So if we have our periodic table, which for this course, you're always going to have one on a quiz or test. You don't need to memorize that periodic table. We just need to know how to ultimately use it. And with the end part of this chapter, we'll start to see how it's organized. And then in one of the later chapters, we'll also see kind of the exact way it's set up so we can use it even more as a tool. But if we're looking at the periodic table, we can find iodine, I should say. Iodide is going to be just this particular -1 charge anion. But we can find iodine, and then once we find it, we can just look to see what the atomic number is. So we can find capital I on the periodic table. We're going to see it's going to have an atomic number of 53. That means it's going to have 53 protons. So if we have a 1- charge, so just note with this, this is just typically the way chemists do it. The way that I'll do it for the most part is put the number and then the charge. So in this case, 1-, we could have 2+, 3-, whatever it may be. If you put -1 instead of 1-, it would be the same thing. So it's not incorrect. It's just this is, for whatever reason, the more common way to show it. But if we have 53 protons and we have a 1- charge, that means we have one additional negative piece. So we've got one additional electron. So we're going to have 54 electrons. And then remember, the mass number is the protons plus the neutrons. The atomic number is just the protons. So if we take the difference between those two, in this case 127, and then again, since it's iodine, the atomic number is just 53. If we take the difference between those two, we'll get 74. So we'll have 53 protons. We'll have 74 neutrons, and then we'll just have 54 electrons. So with this one, if you want to practice with one of your own here, in this case, we've got an ion of platinum with a mass number of 195, and we're told it contains 74 electrons. So we've got different pieces of information here. But we want to figure out how many protons, how many neutrons, and what the charge of this atom are going to be. But with it, we've got enough information in this first sentence to figure out those three pieces of information. So if you want to take a moment on your own to kind of work through it, just pause it. Otherwise, I'm just going to kind of go through how I would approach it so we can see the answer. But with platinum, we know it's platinum. So even without the rest of this information, the mass number, the number of electrons, we can get the number of protons just from that one word of platinum. We can look at our periodic table. It's going to be kind of in the middle of the periodic table, PT. So PT is going to have an atomic number of 78. So we know we've got 78 protons. And then we've got the atomic number now. We already had the mass number. So if we take the difference between those two, 195 minus 78, we're going to get 117 neutrons. And then we already had the electrons. We determined the number of protons. So we had negative pieces to start. We figured out positive pieces just by getting the atomic number of platinum. And since we've got 78 protons, we've got 4 extra positive particles. So we're going to have a charge of +4 there. And again, an ion just means it's going to be positive or negatively charged. With the previous one, if we go back for a second, anion is just a negative ion. So the way I remember it is anion, you can kind of break it down. A, and then this N can just stand for negative. So a negative ion. And then with a positive ion, if we want to be specific rather than just ion, which is general for some charge, doesn't matter if it's positive or negative. But if we wanted to be specific for a positive, like this platinum ion, we could call it a cation. And the way I remember that is cation has the T right in the middle, and that T just kind of looks like a plus sign. Okay. But then with the rest of these here, if you want to take a moment to go through these again, just pause it so you can kind of work through it on your own. This is sort of along the same lines where each of these lines going across represents a particular atom. It might be a little bit simpler here in this case, actually, because I forgot to put in a column for charge. So all of these would just have to be neutral atoms. Otherwise, we don't have enough information to figure out the electron piece of it. And in this case, for the fourth one, we also wouldn't have enough information to figure out the rest of this table if it wasn't a neutral atom and we didn't have the charge provided. But take a moment, pause the video, and then see if, based on the limited information we have here, if you can identify what each of these missing boxes would be, so we can get the full identity, the full description of what that particular atom is going to be. But with it, I'm just going to go through it, so it's just going one by one. If we just had the atomic mass, so if we just had 9 here, that wouldn't be enough information, because we know that's going to be a combination of 9 protons and neutrons, but we could have that combination be in 5 and 4, 6 and 3, whatever it's going to be. So if we just had 9 by itself, that wouldn't be enough. And if we had the capital N here for nitrogen, we could get some of these, but since we have both of those together, we can get all of these different boxes. So since it's nitrogen, we can look at our periodic table, and kind of near the top right, we're going to have that capital N for nitrogen. We can see that it's going to have an atomic number of 7. So we've got 7 protons. And then, like I said, I forgot to put in a column for charge. So we've just got atom here. So these are all going to have to be electrically neutral. So in addition to 7 protons, we'll have 7 electrons. And we can also get the atomic number. And then with the isotope name, that'll just be the element. And then the number at the end, we haven't talked about this yet, is just going to be the mass number. Because if it's nitrogen, we always know it's going to have 7 protons. But we're going to have different versions of some of these atoms, some of these elements. And the difference isn't going to be the number of protons, because that would change the identity of the element. The difference is going to be the number of neutrons. So we'll talk about isotopes, which is what these are going to be, just different versions of those same elements. So same number of protons, different number of neutrons, so a different mass. But we use that number at the end to specify exactly what that mass is going to be. But now for the neutrons here, we've got the atomic mass, we've got the atomic number. It's just going to be the difference between those two. So in this case, just going to be a 2. So nitrogen 9 has 2 neutrons there. With the second one, chromium 54, again, this number here, 54, represents the atomic mass, or the mass number, same thing. So without even the chromium piece, we could get that mass number. But since we have chromium here, we can look at our periodic table, and kind of to the top, kind of in the middle, a little bit off to the left, we've got Cr. So chromium is going to have the symbol Cr. And once we find that spot, we'll have 24 protons, 24 electrons. An atomic number of 24 as well. So the missing piece here again is just the neutrons, but it's just going to be the difference between these two. So we're going to have 30 neutrons. And then with the next one, atomic mass and atomic number. So the difference between those two, again, just our neutrons. So in this case, it's going to be 148. But we've got the atomic number, which is always the number of protons. And since this is a neutral atom, that's the number of electrons as well. And 94 is going to be the symbol Pu, and that's going to be for plutonium. So plutonium 242. And then with these last two, again, kind of the same idea. If we just had neutrons and electrons, but weren't told that this was an atom, the neutrons can differ for an element, so that can never on its own be used to identify it. And if it's not an atom, so it's not neutral, we would need to know the charge so we know exactly how many protons there were. Because with these electrons, it could be a atom that then gained 2 electrons or lost an electron or whatever it may be. But since we do know it's an atom, since we do know it's neutral, we can fill in 46 for the protons, which will be 46 for the atomic number. And that means the atomic mass, that mass number, is just going to be 108, because we're just going to add these two together. And then if we look at the periodic table, 46, kind of in the middle, we're going to have PD this time, and that's going to represent palladium. And then with the atomic mass of 108. And then finally, 7 protons, which means we've got to have 7 electrons for a neutral atom, atomic number of 7, mass number of 15, just because we've got 8 neutrons with those 7 protons. And then this one, just like the first one, has an atomic number of 7. So even though we've got different masses, we have the same number of protons. We're going to have the same element identity, but we've got a different number of neutrons. So we've got 2 different isotopes of that same element. So if we look at the link here, so again, the ones in yellow are just the isotopes because they're both nitrogens, but they've got different masses. Nitrogen 9 was actually recently discovered. So if you go to the notes on Canvas, you can click this link, or I guess you could just type it in if you wanted to just pause it and copy that out. But it just gives more information about that isotope. So it only exists for like fractions of a second, an extremely short amount of time before it breaks down. Just because there's going to be a lot of protons in that nucleus relative to the neutrons. So if you think about positive protons, they're going to repel one another just because the like charges are going to repel. So we need the neutrons there to kind of buffer them almost. But with nitrogen 9, we only have 2 of those neutrons. So it's just going to be a very unstable nucleus. So in quarter 3, when we look at nuclear chemistry, the ratio of protons and neutrons is going to be something we'll focus on to identify if a atom's going to be radioactive or not. And then depending on if the ratio is a lot of protons to neutrons or a lot of neutrons to protons, that'll actually allow us to determine how that radioactive nucleus is going to decay. But kind of along the same lines as the previous one. In this case, though, we've got ions. So these are going to be things with charges. So the first one, fluorine with a negative charge, is going to be an anion. And then gold with a positive charge is going to be a cation. But with this information, we can still figure out the exact number of each of those different subatomic particles. So with fluorine, and again, if you want to pause it, as always, just pause the video. Or if you want to work on it on your own, and as always, pause the video, excuse me. But with fluorine 19, -1 charge, the fluorine allows us to get the atomic number, allows us to get the number of protons. So with fluorine, we're going to have an atomic number of 9. So we're going to have 9 protons. And then since we've got a -1 charge, that means we have an additional electron. We have an extra negative piece. So we'll have 9 protons with 10 electrons. And then with the mass has to add up to 19. So that's protons plus neutrons. We have to get to 19, but we've got 9 protons, which means we're going to have 10 neutrons with it. So we'll have 9 protons and then 10 for the electrons and neutrons. And then similarly with gold 199, based on being gold, we know the atomic number is going to be 79. So if it's 79 protons and then has to add up to 199, that means we'll have 120 neutrons. And if we've got a +3 charge, that means we'll have 76 electrons because we're going to have 3 less than the protons. We're going to have 3, we're going to be missing 3 of these negative pieces basically, and that's where the positive charge is coming from. So again, with these charges, we don't add protons or take away protons in the case of the negative charge, because that would change the element itself. So we can only change the number of electrons, and that's why atomic number is always equal to protons. But we can have a different number of neutrons in terms of the isotopes, and we can have a different number of electrons depending on the particular charge for those atoms. Okay, and then with this next piece, I'm going to go through it kind of quickly just because it's, I think, mostly straightforward. But if you do ever have questions, as always, just let me know. We can meet during office hours or some other time just to go through any of that material. But with these elements, the periodic table, you can see each of these elements have a symbol that's either 1 or 2 letters. And in the case of something like carbon or oxygen, like nitrogen even, and quite a few of the elements, it's just a single letter. And if that's the case, we're just going to capitalize it. But then we also have a whole bunch of elements that are going to have 2 letters to them. And in that case, it's going to be important that we use the proper notation. So we always capitalize that first letter. And then in the case of something like cobalt, if we have a second letter in that symbol, we always want to make sure that we put it lowercase. And the reason we do that is because if we're referring to cobalt, but we use the notation capital C, capital O, that's no longer referring to cobalt. Now that's telling us instead of 1 cobalt atom, we've got 1 carbon with 1 oxygen. And that would actually represent carbon monoxide. So that's going to be a deadly gas. So if you think about your car in the wintertime, sometimes people heat them up just so that it's warm when they get in there. But the car itself is going to be less efficient. 1, at colder temperatures, and then 2, just when you first turn it on. So instead of producing carbon dioxide, you're going to get a larger percentage, or a relatively larger percentage than normal, of carbon monoxide. And that's why in the wintertime, there's often quite a few people that pass away from carbon monoxide poisoning, because the carbon monoxide actually binds to the hemoglobin in the blood, and it binds much better than oxygen does. So now your cells just aren't getting the oxygen they need. You essentially just get sleepy, and then ultimately it can become worse, become fatal, depending on how long you're exposed for. Whereas cobalt, again, same letters, just lowercase o versus the capital one. This is going to be a metal. It's going to be used in batteries, alloys, sometimes like stained glass and things like that. So even though they look very similar in terms of the sort of notation, these are going to be 2 very, very different substances. So it's going to be important that we use that proper notation. So if we're looking at cobalt, if we're looking at any of those elements with a 2-letter symbol, it's going to be important that we lowercase, keep the second letter lowercase. Excuse me. Okay. And then just looking at the symbols here, you can see a lot of them kind of match up with what you'd expect. Neon, Ne, nickel, Ni, nitrogen, N, oxygen, O, phosphorus, P, platinum, PT. But we see mercury, Hg, we see potassium, K, silver, Ag, lead, Pb, iron, Fe. So we see a whole bunch that don't really match up or don't really match up well. You can see copper, Cu, so the C kind of makes sense. U's nowhere there. So just with some of these elements that don't have a symbol that really matches its name like you'd expect, those are just going to come from the Latin name. So it's something like lead, that's going to be based on plumbum. So where's that? Right up here. So if you think about plumbers, that's going to be the source of that name. A lot of times pipes are made of lead, or at least have some amount of lead in them. So one of the issues with Flint, Michigan is going to be the lead in the pipes. So originally they were taking water from the Detroit River, which was fine, but then they switched to the Flint River in a cost-cutting decision. But the Flint River is much more corrosive. So with those lead pipes, a lot of the times they're not actually really too much of a problem, because essentially you have sort of a layer build up on the inside of the pipes that kind of actually sort of isolates the pipe itself from the water that's moving through. But when they switched to the Flint River, that more corrosive water, it actually sort of damaged that layer. And then they wound up having lead make its way into that water. There was other issues as well, but that was one of the big ones. And it's, at least I haven't heard anything new about it, but I believe that they still don't have clean water to drink in Flint, Michigan. But then with some of these other ones as well, you can kind of just see the Latin names there. And then just to go back for a second, you can see tungsten is capital W, but that's just going to be from the Germanic name Wolfram. And with it, again, you always have a periodic table in this class, so you don't need to memorize any of these. Some of them you'll just become extremely familiar with if you're not already. But you don't have to memorize those. But in addition to the symbol with just the letters, so He in this case for helium or Mg for magnesium, we can also include numbers to give us more detailed information about that particular atom. Because like I said, we can have, and like we saw earlier, we could have nitrogen with a mass of 9, or we could have nitrogen with a mass of 15. So if we look at the examples here, there's going to be, depending on where we put those numbers, they represent particular pieces of information. So with the top left here, that's always going to be the mass number. And if we're writing the notation like we see here, this isotope symbol, that mass number always has to be present, so we know exactly which version of this isotope we're dealing with. In terms of the charge, that's just going to go on the top right. So in this case, helium with a 2+ charge is telling me that it lost both of its electrons. So helium only has 2 electrons to begin with. So if we've got a +2 helium, it just lost both of those electrons. So this would actually just be what's known as the alpha particle. So what they used in some of those experiments for the subatomic particles. But if we have a charge, we always make sure to include that. So whether it's positive or negative, we can put that information there. But if we have a charge at all, we always put that information in. If it's a neutral atom, you can exclude that. Sometimes people write the 0 in just to make it explicit. But if there's nothing written in that top right, we just assume that it's going to be neutral, because otherwise we have to put that information in. And then with the bottom left, this is the atomic number. So you can see often omitted or sometimes omitted, because with it, that number is somewhat redundant as long as we have the symbol there. So if we think about helium, He, any helium atom, any helium ion is always going to have 2 protons. So if we put the information there, it's good, just because if we don't know that particular element, we don't have to then go back to the periodic table. But just by having the symbol itself, we automatically know, or we can find out, that there's going to be 2 protons. Same thing with magnesium and 12 protons, atomic number of 12. But with the masses, we could have helium with a mass of 3. We could have magnesium with a mass of 23 or whatever it may be. So that can change. But if it's Mg, the atomic number is always 12. If it's helium, the atomic number is always 2. So sometimes they just don't put that information in. And then with the bottom right corner, if we do have a number there, that we'll see when we look at the chemical formulas for compounds. But what that's referring to is just the number of those atoms. So you can kind of think of these 3 pieces of information, these 3 numbers, as referring to information on what type of atom this is. Whereas if we have a number on the bottom right, that's going to tell us how many of those atoms do we have. And if we look at these very light isotopes, you can see hydrogen actually has sort of specific names for its isotopes, so protium, deuterium, and tritium, just based on the mass of 1, 2, and 3. The other ones we would just call like helium-3 or lithium-7, boron-10, beryllium-9, whatever it is. But if you look at the periodic table, you'll see that with these elements, some of them are going to be close to some of them in particular. But if you look at lithium, for instance, the atomic mass on the periodic table isn't actually going to match either of these values. Same thing with boron. And if we look at the other ones as well. And the reason for that is because the atomic mass on the periodic table is going to be a weighted average based on the natural abundance. So if we think about an average in general, we would just go through, add up the masses here, and then just divide by the total number of isotopes for that atom. So for carbon, we do 12 plus 13.0034, 14.0032, and then divide by 3. And if you think about it, this is basically 12, 13, and 14 exactly. So if we add those up, divide by 3, we would just get 13. But because it's a weighted average, it's also considering how often these different isotopes appear naturally. Because with these different nuclei, they're going to have a different level of stability. We're going to have a different ratio of these isotopes to one another. So it's not just going to be an even split. You can see in a lot of cases, we have pretty much all of it as one isotope and then just a small amount as the others. And that's why with something like carbon, the atomic mass on the periodic table is going to be 12.01 or 12.011, depending on how many digits that periodic table goes to. And the reason for that is because in addition to taking into account the masses here, it's factoring in how often do they appear. So since pretty much all carbon, 99% of it basically, is carbon-12, the weighted average is going to be 12.01 there. And similarly with nitrogen, you can see these 2 isotopes, basically 14 and 15. But the atomic mass in the periodic table is going to be like 14.01 or 14.007, depending on which periodic table you're looking at. And the reason for that is because 99.63% of nitrogen is going to come from nitrogen 14. So if we think about if we had, for instance, 1 million atoms of nitrogen, they'd either have one of these 2 masses. But then if we took the average mass of all 1 million of those atoms, the average mass wouldn't actually be either of these. It's going to be 14.007. So it's going to be much closer to this one since we have so many of those relative to the other isotope. But it's not going to be exactly that. And with it, we can see the equation here. So essentially what this is showing is sigma, this summation, is just telling us we're going to do this calculation for every single isotope we have, or every natural isotope, I should say, that we have for that element. So for boron down here, what this is showing is if we had 80%, 80.1% of boron-10, or rather, oops, never mind, 19.9% of boron-10 with a mass of 10.0129 atomic mass units. And then the other 80.1% is going to be boron-11. We want to figure out the average atomic mass. So we're not just going to add those up and divide by 2. Now we're going to factor in the amount or the fractional abundance of each of those isotopes. So we turn the percentages just into decimals. So move that decimal to the left 2, or you could plug in 19.9 divided by 100. It'd be the same thing. But notice the average atomic mass that we saw for here, 10.81. If we had a sample of boron with a billion, if we had any number of atoms in there, none of those individual atoms would weigh 10.81. But because with that sample, we know the fractional abundance of each of those isotopes, we know that the average mass of all of those atoms is going to be 10.81 AMUs. But again, if we were to pick any atom individually, we would have basically an 80% chance to get one that weighs 11, a 20% chance to get one that weighs 10, but the average of all of those would be 10.81. So you can kind of think about it, for every 5 boron atoms, 4 of them are going to be boron 11, and that 5th will be boron 10. So that's why the average is closer to boron 11. We have more of those atoms, so we factor, or we weigh that isotope more heavily in the calculation. And with these types of questions, we don't want to just automatically assume. So if we're given a question like this, where we want to figure out the average atomic mass or the average mass of neon, we don't want to automatically look at the periodic table and just take whatever that value is. Because depending on the source, so in this case, it's referring to a solar wind. So the neon is coming from outer space with the meteorite. We could have a different fractional abundance. So the source itself could affect the ratio of these different isotopes. So we don't want to just look at the periodic table and take that value. What we can do, though, just to get a rough estimate of where that number should be, is we can look at the mass of those different isotopes. And even though it's a weighted average, the weighted average still has to fall somewhere in this range. So in this case, the lightest isotope is just under 20. The heaviest isotope is just under 22. So we know the weighted average is going to have to fall somewhere in that range, somewhere between those two values. But because we've got almost all of it as neon 20, as this lightest isotope, we should expect that our answer is going to be much closer to this value than the other two. So we can, in our heads, just kind of think about what this should be, just so that when we get our answer, we can kind of already have an idea if that makes sense or not. But with this one, just like the previous one with boron, we're going to have a different parenthesis essentially for each of these isotopes. So we'll change these percentages just into decimal values. So we'll move the decimal left 2, and then we'll multiply it by the mass itself. So if we look at the one here, again, 91.84% just becomes 0.9184 or 0.0047, 0.0769. And then we're just multiplying each of those by the atomic mass of that particular isotope. So when we multiply and then add those all up, we get 20.15 atomic mass units. And like I said, it's going to be somewhere in the range from the lightest isotope to the heaviest one. But because we've got a large majority of the neon atoms existing as this lightest isotope, we should have the weighted average be much closer to that one. And that's exactly what we see here. 20.15, so it's just a little bit heavier than this lightest one. Still pretty far from the other two, though. So we can be confident in that value just because it kind of makes sense with what we'd expect. But like I said, we don't want to just necessarily look at the periodic table because terrestrial neon, so neon from Earth, so terrestrial just referring to Earth, Terra, terrestrial neon is going to have an atomic mass of 20.18 AMU. So because we've got different sources of this element, we're going to have a different fractional abundance, so we can see a slightly different average mass there. Right. And then if you want to practice with this one, just go ahead. It's going to be kind of the same thing. In this case, we've got 3 magnesium isotopes, 24, 25, 26. But we still have the percentages. We still have the mass of each of those isotopes. So we can move the decimal left 2 for the percentage, just multiply it by the mass, and add all those up. And we're going to see we'll have an average mass of 24.31 AMU. Okay, but with this one, we've got a little bit of a different type of question. Let me do it like this. Insert equation, new equation. So if we think about how we can set this one up, we're going to have a parenthesis for chlorine 35 plus, oops, we'll have a parenthesis for chlorine 37. And then with it, in this case, we already know what this is going to add up to. So if we go through and think about what these parentheses are, they're the fractional abundance times the mass of that isotope itself. So for the first one, I'll just do X times 34.96885 AMU, because we don't actually know how much of this isotope we have relative to the other. And then for the next one, I'll kind of do the same thing, but I'll just use Y to represent the percentage there, or the fractional abundance, I should say. 96590 AMU. So it's not critical that you include the unit in the calculation, but I always like to, just so we can make sure what we know what we're kind of working with in each particular step. But with it, now we've got two different variables in a single equation. We can't solve for those. If you think about it, we could just make up some number for y and then solve for x, or we could make up some number for x and solve for y. But depending on what we make up for that one variable will determine the other. And that first one's just arbitrary. So we can't just willy-nilly plug in whatever values we want. But if we think about these percentages, if we go back to this one, for example, 78.7%, 10.13%, 11.17%. So if we add these up, 78.70 plus 10.13, that'll give us 88.83%. And then if we take 88.83% and add 11.17 to it, we just get 100. Because with these percentages, they're going to represent all of the natural isotopes of that element. So they have to add up to 100% overall. So what we can do here is set up a second equation. But instead of having it equal 100, I'm just going to have it equal 1. Because remember, with these fractional abundances, we plug them in as decimals anyway. We could have this equal to 100, but it would just kind of throw off this actual step of it. So we just want to think about x plus y as these fractional abundance values rather than the percentages themselves. But with this one now, x plus y is equal to 100. We still have two variables in one equation, but now we've got the same two variables in both of these equations. So what we can do is rearrange this bottom one in terms of the top. And with it, I can't remember what is on the next one. If it's, I think it's this. But if we rearrange this to solve for y, so we can subtract x from both sides, now what we can do is take this 1 minus x and just plug it into our equation for y. Do 1.0 minus x, capital X. Because now what we have, let me copy this. What we can now do is, so I'm going to get rid of the units just so it's not as clunky. But we can just combine those to 34.96885x, just multiply those together. And then what we'll see is 1 times this value. So we're going to distribute this to everything in the parentheses. So 1 times that value is the same. And then if we distribute it to the x, what we're going to see is so now at this point, we've got just one variable. We've got it in two spots, but we've got one variable. We can combine those. We can subtract this 36.95, 96590 number from both sides, and then just solve for x. So with it, that's going to be, let's see, 34.96885 minus 36.96590. So we'll get 1.99705x is equal to 35.453 minus 36.96590. Zero instead of a decimal. Negative 1.5129. So again, with it, I just combined both of these x's together. We wound up with a negative number because 36 is bigger than 34, and we have the negative there. And then the same thing, I just subtracted 36.96590 from both sides. So what I'm going to do is just get rid of the negative on both of these. So then we can do divide both sides by 1.99705. And 705. And we get x is equal to 75.76%. So then if we want to get the y one, we can go back to our original equation, or one of our earlier equations, I should say. But now we actually have x. Just remember, we're going to have this as, oh, I actually converted it to the percentage, so it really should just be 0.7576. But we're just going to plug it in as 0.7576. So we'll have y is equal to 0.2424. Hopefully I got the correct numbers there. Perfect. Yep. So I can still do math. But yeah, this is showing just the same thing. And again, the reason this works is because we only have 2 isotopes here. If we had a third isotope, we wouldn't be able to do this step unless we knew the abundance of one of those isotopes. So if we had 3 of them and we were told one of them is 20, we could kind of set this equal to 0.8 rather than 1, and then kind of go through the same process there. But if we have 3 unknowns, we can't possibly solve without additional information. So if you want to practice with this one, kind of be the same idea here. Just naturally occurring isotopes of copper in this case, but it'll be that same sort of setup. So I'll just kind of start going through it. We'll have parenthesis x times 62.9296, and I'm just going to leave out the AMU just to make it easier. But y times 64.9278, and then we know this is equal to 63.456546, excuse me. But again, we can do 1.0 minus x is equal to y. So when we go to plug this in, we'll do this. Instead of y, we'll have, let's see, 1.00 minus x. But then when we distribute that, we'll have, oops, I did not copy the second one again. But we'll have that as our first piece. And then with the second one, if we just think about this parenthesis, we'll have the 64.9 number times 1. So we'll just have that same value. And then we'll have 64.9278 x there. Oops. So when we go through and what is happening? When we go through and actually 64.9278 62.9296. So we'll get negative 1.9982x. So just combining these two terms together with the x's. And then again, I'm going to subtract this 60. We don't really need these parentheses here anymore. So just to make it a little bit more clear what's going on. So I just combined both of the terms with x. Got that negative 1.9982x. And then with the other ones, 63.546 minus 64.9278 equals negative 1.3818. But again, we've got negative on both sides. I'm just going to get rid of that to make it simpler. We'll now divide both sides by that 1.9982 value. And when we do that, we'll get 1.9982. We'll get 0.6915. That'll be 69.15% for the copper 63. So I'll just do Cu 63. And then for Y, that'll just be 1 minus that value. So that'll be 0.3085, which means we'll have, 30.85% copper 65. So again, same idea as the previous one, just different values, because we're looking at copper in this case instead of, what was the other one, chlorine. But it's still that same idea where if we've got two of them, two of these isotopes, they have to add up to 100% overall. So we can set x plus y is equal to 1, rearrange it to just get it in terms of y, and then plug that into our original equation, our fractional abundance, and just go through and solve for that. Just doing a little bit of algebra at that point. And then that is the same thing I got. So again, still able to do math, which is always a good sign. But with these, what's a good stop point? We'll go just a little bit further to continue with these isotopes. Because with it, you might be wondering, what are these important for? Why do we care? What is the difference between different isotopes? And then how do we even distinguish between those? So the reason that these isotopes are going to be important is because they'll have, in some cases, applications in different fields. So when we look at nuclear chemistry, we'll really dive into this. But medicinally, there's iodine, which can be used to then collect in the thyroid, so it can be imaged. There's other medicinal uses. There's nuclear energy, nuclear weapons, radioactive dating in terms of like carbon dating to see how old a fossil was, looking at two different isotopes of carbon, the ratio of those to one another, and doing a calculation to go back. And then also environmentally, we can use the ratio of two different oxygen isotopes to get an understanding of what the weather, what the climate was like in the past. So if you think about these two different oxygen isotopes, we could have H2O, where that oxygen is an oxygen 18, or we could have H2O, where that oxygen is an oxygen 16. So this is actually kind of a weird formula, the way they're showing this, because normally that number would be on the left side. But if we put it there, in this case, it would just be kind of difficult to read. So with this one, we're just making kind of an exception for how we note that. But with these isotopes, a lot of isotopes of an element are going to have very similar chemical properties. But because they've got different masses, there will be different physical properties. And the rate of evaporation for oxygen 16 versus oxygen 18 is actually going to be different. So what we're going to see is oxygen 16 is going to more readily evaporate. And then oxygen 18, once we have both of those in the atmosphere, oxygen 18 is actually going to more readily get deposited in precipitation. So we're going to have more oxygen 16 in the atmosphere in general. But what we can do is actually look at ice core samples. So if you think about going to the Antarctic or the Arctic, anywhere where there's a lot of snow, especially where that snow doesn't really melt, it's essentially a catalog into the past, because what they can do is take ice cores at different depths, and then just basically the further down you go in that ice, the further back in time you're looking. And in the ice, there's actually air bubbles that are going to have water vapor, that are going to have oxygen just kind of trapped in it. So what they can do is look at the ratio of oxygen 18 to oxygen 16. And based on that ratio, they can do a series of calculations to kind of determine what the weather was like in the past, or what the temperature was like in the past, I should say, I guess. And with it, the calcium carbonate, so CaCO3, in shells, so different shelled organisms. The shells themselves are typically composed of calcium carbonate, so that's one of the reasons climate change, ocean acidification is a problem, is because it affects how much calcium carbonate is available, how strong their shells are. But just to go back to the oxygen isotopes, like I said, we can use the ratio of those two to get an understanding of what the temperature was like. Because at different temperatures, we'll have a different ratio of those isotopes, basically. And with it, this is a important piece in understanding kind of the history of Earth. So we do have cyclical periods of heating and cooling within the lifetime of Earth. So a lot of the times climate change deniers, I should say, point to that as evidence that global warming isn't man-made, it's not caused by burning fossil fuels, because they point to that cyclical heating and cooling. But what they also ignore is the fact that we have extremely high CO2 concentrations, so higher than ever, and the fact that the temperature is rising drastically as well. But with these isotopes, in addition to those other uses that we'll really dive into in the nuclear chemistry chapter, we can also use these to understand the climate, understand how the Earth kind of was in terms of temperature and other environmental factors in the past. And then also with these isotopes, just to think about how can we actually detect them. Like I said, we're going to have very similar chemical properties with these different isotopes. So in order to examine them or differentiate them, the only thing we can really focus on a lot of the times is going to be the mass. So what we can use to separate them and what we can use to determine the abundance of these isotopes relative to one another is just what's known as a mass spectrometer, sometimes just an MS. And this is something I actually used in my graduate research, not for particular isotopes. We did actually use, in some cases, radioactive isotopes to make sure that a sample we were adding to something was just coming from us. So we could use an isotope that we wouldn't find in the environment naturally, just so we can make sure that that sample was being added from us and not just something that was already there. But the way this mass spectrometer works is, so we have the sample inlet, basically just gives us our sample, and then we heat it up extremely quickly. So we vaporize it into the gas phase, and then we've got something that's going to essentially ionize these substances. And depending on the substance that you're actually analyzing, this whole process is going to look different. So there's kind of different types of ionization, different hookups essentially to the mass spectrometer itself. But what this does is it gives us positive particles. And now that we have a charge, we can accelerate those particles. And using a magnet, they're actually going to deflect. They're going to change course slightly based on the mass. So M over Z is just the mass to charge ratio. So if you think about it, if we had zirconium, Zr, all of these are going to have the same number of protons, but we're going to have a different number of neutrons. So we've got these different masses. So if we make all of them +1 or +2, whatever it's going to be, as long as they lose the same number of electrons, they're going to have a different mass to charge ratio. And with that, that means they're going to take a different amount of time to reach the detector. So a zirconium-90 is going to take a different path than a zirconium-91, is going to take a different path than zirconium-92, and the same thing with 94, 96. So that's what we're showing with these different lines here. And then based on that, based on the amount of time it takes. In some cases, there's other detection methods, but we can use that to identify these particular isotopes. And then with mass spectrometers, there's a whole bunch more detail. Like I said, the type of sample you're using is going to be important in terms of kind of how we have everything set up, depending on what detector we use. In some cases, we actually kind of hook up multiple mass spectrometers together. So there's a whole bunch of things we can use mass spectrometry for. It's probably one of the most powerful instruments in chemistry, just because it allows us to analyze a whole bunch of different substances. And with it, we're just seeing 90, 91, 92, 94, 96 here. But depending on the mass spectrometer, depending on the detector, the sample, a whole bunch of other factors, they can actually determine differences in mass discharge to just very, very precise levels. But with the next one, we'll start to look at chemical formulas and how we can kind of represent different substances when we start to take those atoms and just bond them together. But we'll wrap it up here for now.